everyone, my name is SYAMIMI and I will explain about introduction. Impedance spectroscopy is a key technique for measuring the resistance and capacitance in RC circuits by applying an alternating current signal across a range of frequencies and analyzing the impedance response. This method provides valuable insight into the resistive and capacitive properties of the circuits, accurate determination of resistance and capacitance without relying on DC measurements or assuming linear behavior. Widely used in material science, bioengineering, and electronics, impedance spectroscopy offers a deeper understanding of RC circuits' electrical properties in both theoretical and practice application. Next, I will explain about problem statement. Accurately measuring resistance and capacitance values in RC circuit is a crucial for understanding their behavior in electronic application. Traditional methods like DC measurement often fail to capture the frequency-dependent nature of impedance. Impedance spectroscopy offers a more comprehensive, non-invasive approach, but challenges remain in interpreting complex impedance data and extreme accurate RNC values. This study to address this challenge by analyzing impedance across a broad frequency range, identifying potential source of error and comparing the result with multimeter measurements. The goal is to demonstrate the feasibility and advantage of impedance spectroscopy for practice RC circuits characterization in both laboratory and practical settings. And lastly, this is our hypothesis. The first one is impedance spectroscopy will prove to be more effective tools for measuring resistance and capacitance in complex or non-ideal RC circuits compared to traditional methods, especially in situations where circuit elements are non-linear or affected by environmental conditions. Second one is impedance spectroscopy will provide more accurate measurements of resistance and capacitance in RC circuits compared to traditional DC measurement techniques, especially in circuits with non-ideal or frequency-dependent behavior. And last one is the accuracy of impedance spectroscopy method will be influenced by factors such as measurements, frequency range, signal and amplitude, and the precision of measurement equipment.
Now we move to literature review. The first for literature review is fundamental concept of EIS for measuring RC circuit parameters. Principle of impedance spectroscopy. Impedance spectroscopy is a general term that subsumes the small signal measurement of the linear electrical response of the materials of interest, including electrode effects, and the subsequent analysis of the response to yield useful information about the physiochemical properties of the system. Moreover, electrochemical impedance spectroscopy enables the examination of the electrochemical nature of electrodes and electrochemical cells by applying an alternating voltage or current and measuring the resulting current or voltage. Principle of RC circuit. An RC circuit is a simple electrical circuit consisting of a resistor and a capacitor connected to a power source. These circuits are widely used in electronics for their ability to control the flow and storage of electrical energy. In an RC circuit, the capacitor charges up to the voltage of the power source through the resistor, which slows down the rate of charging. When the power supply is disconnected, the capacitor discharges and it stores energy flow through the resistor, gradually decreasing the voltage. The charging and discharging processes follow an exponential pattern determined by the time constant, which is the product of the resistance and capacitance. RC circuit can be arranged in series or parallel, and they play a crucial role in many applications like filters, timers, and power supplies moving. By adjusting the resistor and capacitor values, engineers can design circuits for specific purpose such as high-pass or low-pass filters and timing circuits. The third one is advantages of impedance spectroscopy for characterizing RC circuits. Accurate characterization of RC circuit elements. Impedance is the measure of the opposition that a circuit presents to the passage of a current when a voltage is applied. Rather than solving the differential equation relating to circuit that contain resistor and capacitor, we can imagine all sources in the circuits are complex exponential, having the same frequency. The phase of the complex impedance is the phase shift by which the current is ahead of the voltage. Next, limitation and challenges in measuring resistance and capacitance in RC circuits using impedance spectroscopy. System performance may decline over time and become less reliable. IS works by applying an alternating current signal at different frequency to the circuit and measuring how the circuit responds. This response is used to determine the resistance and capacitance. However, the accuracy of this measurement can be affected by several factors. For example, the electrodes used in the measurement can get damaged over time or gather dust and dirt, leading to incorrect readings. The last one is future directions in IS for RC circuits. IS is a powerful analytical technique widely used to characterize the resistive and capacitive properties of electrical circuits, especially RC circuits. IS has proven effective in various fields, including material science, biology, and battery diagnostic, due to its ability to provide insight into a system's impedance over a range of frequencies. However, ongoing research aims to expand the application and improve the precision of IS in RC circuits, with emerging studies focusing on advancement in measurement accuracy, integration with machine learning, and application in complex systems.
I am going to talk about methodology of our mini project. The experiment that measures resistance and capacitance value of RC circuits using impedance spectroscopy started with the preparation. Circuit setup will assemble the RC circuit ensuring precise connection using two components which are capacitor and resistor. Ensure all connections are firm and use low resistance leads to reduce measurement errors and record nominal values of R and C for comparison with measured results. Next, using electrochemical impedance spectroscopy, this device can measure impedance over a range of frequencies. Then, the calibration that calibrate the measurement system using standard components to reduce systematic errors. Perform short circuit calibration on the analyzer to eliminate baseline errors by using a resistor and capacitor with known values to validate the measurement system. For IS measurement procedure, first connect the circuit to the impedance analyzer, then select the appropriate frequency range and sweep parameters. The last step was to run the sweep to measure impedance value Z across all chosen frequencies. The validation of data can be proved by theoretical comparison, which is compare experimental value of R and C with theoretical predictions. Next, repeatability test. Repeat measurements under identical conditions to ensure consistent results and to calculate error quantification by calculating the percentage error between nominal and measured values. Now, we move to results. We measured the resistor using color code and digital multimeter. With digital multimeter, we got 10 ohm. By using color code, we got range 5 to 15 ohm. To get Z value, we use formula ZR square plus XL minus XC square. R is a resistor value, while XC have its own formula which is 1 over 2 pi FC. F is a constant value which is 3.3 times 10 power of 15 Hz. C is a value of capacitor. Then we can substitute all the information into the Z formula. Thus, the Z value we get is 10 ohm. This plot show the impedance response of system. The x-axis represent the real part of the impedance, while the y-axis represent the negative imaginary part of the impedance.
Now, we are going to talk about discussion. The Nyquist plot shows how the impedance of a system changes using experimental data, which is black dots, and a fit curve, which is red line, based on a circuit model shown in the inset. The circuit has a resistor in series with a parallel combination of another resistor and a constant phase element. In the graph, the x-axis represents the real part of impedance, while the y-axis shows the negative imaginary part. The plot forms a semicircle, which is common in systems with one time constant. The semicircle's width, which is diameter, represents R1, which is the resistance related to charge transfer or bulk properties. At high frequencies, which is lower left corner of the semicircle, the impedance is dominated by resistive behavior of R1, while the impedance is at its lowest. At lower frequencies, which is at the top of the semicircle, the imaginary part acts more like a capacitor because of Q1. The tail on the right shows how the system behaves at very low frequencies. So this is how we calculate the impedance, capacitance, and circuit impedance. For conclusion, we successfully measured the resistance and capacitance of RC circuits using impedance spectroscopy. The Nyquist plot showed a semicircular curve indicating a single time constant, with R1 representing resistance and Q1 accounting for non-ideal behaviors like surface roughness. The resistor color code gave the theoretical value of 10 plus minus 5% ohms, and it matched with the DMM measurements result, which is 10 ohms. Impedance, we got the impedance was 10 ohms with capacitive reactance at C of 1.557 multiple to 10 power of negative 17 ohms and 3.3 multiple to 10 power of 15 Hz and 3.097 Fahrenheit. The Nyquist plot showed impedance, we got the 10.2 ohms with an error of 0.2 ohms only. Despite minor errors, the expected values match the theoretical ones, proving the method works. It suggested to use better equipment like precise tools and higher quality components to reduce errors and to make sure the setup is done properly to avoid mistakes caused by outsider factors. The project showed the usefulness of impedance spectroscopy in analyzing RC circuits, emphasizing setup, precision, and theory comparison through Nyquist plots and circuit models.